Hello everyone. Today I'm going to show you something that I've been working on. It's a smart chatbot that can actually read and answer questions from your PDF. You know how sometimes you have these really long documents, which are more than 600 pages of medical documents, or certain research papers, or even school children's PDF notes, and you just want one quick answer. So instead of scrolling and searching manually, you can just ask the bot that, and it'll fetch the right answer for you, like a person assistant. So what's cool about what I have done? It's like I have provided it two kinds of brain power. One is Qwen 2.5, which runs completely on your laptop, so you don't have to send any of your data anywhere. And the other option is OpenAI's GPT model, which are a bit more powerful, especially when it comes to generating polished answers. And they work through the internet and they require API key. So you can switch between them inside the app depending on whether you want more accuracy or just privacy. So now what is the flow, I will tell you. So you first of all upload the PDF, then it reads and splits the contents in the chunks, splits into chunks, and then converts those chunks into embeddings. And when you ask a question, it compares your query with the chunks and picks up the most relevant one, and then it passes that context into either Qwen or OpenAI, and they generate the final answer for you. So everything happens inside the Streamlit app. So it's a clean chat based experience where you upload your file, ask questions, and get the replies. So in this session, I'll walk you through the entire flow, how the backend works, what happens when you ask something, or how your model figures out what to answer. And I will also start now with the architecture, and then we'll jump on to uploading the first PDF. Okay, so now I am going to walk you through my project on building this RAG pipeline for effective document based querying using the large language models. And this primary goal of this project is to help the users easily upload the PDFs, ask content aware questions, ensure that the LLM provides accurate, relevant responses based on the document content. So the first step is very crucial. It is PDF ingestion and chunking. So here I take the user's PDF and break it down into smaller manageable chunks, and this is done to help the system digest the content better. Think of it like cutting up a long text into bit-sized pieces so that AI can process them easily. And I load the text from the PDF and split it into chunks of set size, and I'm using the window overlapping method of chunking to make sure that the system captures the context very well. Okay, so now the next step is embedding generation. So this next embedding generation step is where each chunk of the text is turned into a vector, a numerical representation that captures its meaning. So by converting the text into embeddings, I make it easier to compare and find similar pieces of information. And for along with text, I also have images in the data. So in images, for extracting images, I am using OCR technique. Okay, and what I do is I store all these embeddings and metadata. So whenever a user asks questions later on, I can quickly retrieve the most relevant part of the document. Now comes semantic search. So now this is actually the most exciting part. Whenever the user asks a question, the system needs to figure out which chunk of the document are most relevant to the query. So I use cosine similarity to capture the user's query against the stored embeddings and find the top 3 matching chunks. So this step is actually all about ensuring that AI is pulling only the most relevant pieces of information from the document. Then the next step is prompt construction and response generation. So once we have all the top chunks, the next step is actually prompt construction and response generation. So I built a very well formatted prompt that we will see that includes the user's question and the most relevant document chunks, and this prompt is then sent to Qwen LLM to generate a response. If a chunk is missing or is irrelevant, then the model is programmed to respond as no information found, so that the user always know that you cannot depend on AI. It is all generated using PDF only. Okay, AI is not generating anything on its own, so there will be very less hallucinations. In fact, zero hallucinations. And the last step is my local deployment. So I set up a simple local user interface called as Streamlit. This allows the users actually to upload the PDF and type in their questions all in one place, and the magic then happens behind the scenes, and where the app handles the chunking, embedding, semantic search, prompt generation, response creation, everything very seamlessly. And then there are certain post deployment key challenges also. So after deployment, I focused on addressing certain key challenges to make sure that the system performs very well in real world use cases also. So for this, there are a few challenges. The first one I have mentioned is deviation detection. So like if a chunk is missing or doesn't match well, then the system detects this and responds accordingly. Then there's entity extraction and classification. So in future, I plan to integrate certain NLP techniques to extract the structured information like dates and amounts of text also. Then sometimes it is slow retrieval process. So I have optimized retrieval speed by limiting the number of chunks to top 3 pre-computed embeddings, as well as along with Qwen I have given the option to use OpenAI also, especially in this case for speed issues. And finally, the privacy constraint, right? The privacy and monitoring that you have. So all the data that is there is stored locally, ensuring that your user's PDF and the query data are kept private. So overall, this project is basically it is locally deployed, and let's actually start. I'm first going to show you the output after this, and then we will look into the code. Okay. So I will first of all show you the entire output. Okay. So I have created what and how your output will look like. That's what we will see. Sorry. And then I'll show you how the code will look like. Okay? So this is what opens, and we select OpenAI because I want it to be quick right now. So I have Qwen, my local LLM, as well as the cloud LLM. Now what I will do is I will have a simple PDF attached. I have one small moon.pdf. It has information about moon and certain phases of moon. So this is a very small PDF right now that I have taken. It says about the Earth and the Moon's distance. It says about there's no atmosphere. It says about its giant impact hypothesis. Talks about Apollo 11. Talks about the gravity of the which causes ocean tides on Earth. It talks about it never receives sunlight and just water ice has been detected in these craters on some parts. Then there is a image of different phases of moon, and then it has some description of the phases which are new moon, waxing, full moon, third quarter, all of these. So now I'm going to upload this document and we will ask certain questions to the PDF, and after that we will also check if it is hallucinating, even if we are using OpenAI, whether it is really using any other its own information, because I particularly want to create something that will answer only based on this PDF. Okay, so I have already dragged and pulled up the file, and here comes my chat bot. I say hi and it was to answer. Hello, how can I assist you today? Tell me about the distance between. Are you able to see it, or I should just increase the font? Distance between Earth and Moon. Yeah, it is pulling up the answers. Then tell me about say Apollo 11. Yeah, Apollo 11 was a mission that brought certain samples to Earth. Now tell me or show me the image of different phases of the moon. Yeah, it has brought up the different phases of the moon and has also given a small explanation. Now tell or explain this image. Yeah, it is explaining the image. Now I ask, okay, now tell me, now let's see if it is hallucinating. Tell me if who is the Prime Minister of India. Yeah, this information was not there in the PDF, so I'm expecting that this chatbot will not answer my question. Right? Let's see. Yeah, it says, I'm sorry, I cannot provide this real-time information such as the current Prime Minister of India. So if you see that this is the answers that we are drawing out. If I use Qwen, it will only take a lot of time. The amount of latency is much higher in Qwen than in OpenAI. And I will also show you running how Qwen is actually downloaded and used, and we will also check how our question answering is happening using Qwen also. Okay, using code. Okay, fine. Let's go to the code now. Okay, so first what we do is we start by creating a project folder. This is where we'll keep all our project files organized. It is as simple as creating a directory with the command mk directory. Once that is done, then we will move on to cloning the llama.cpp repository. This is the C++ inference engine. We'll need to run the Qwen model. we use the git clone command to get the latest code and place it in our project folder. Next, we need to build the llama.cpp. We use cmake and we compile the code to generate the necessary binaries. This is done by using commands cmake and cmake build, which ensures everything is set up correctly on our system. After building the program, we will create models folder. This folder will store the Qwen model, keeping all the things organized. Now at this point, if the model is already available, we just download the model directly using curl, and if it is not there yet, we will download it using git lfs from Hugging Face. But in our case, we already have the model, so we just have to put it in the models folder. Next, we will install git lfs, and which is necessary for handling large files from repositories like Hugging Face. And once it's installed, we will use it to ensure that the model is downloaded correctly. This is in case we don't have it. Okay, so after that, we log into Hugging Face using our token, and this gives us the necessary permissions to access and download the model files. If we still don't have the model, we will clone the model repository from Hugging Face. We will use git and git lfs for this. It's important that we make sure that we logged in and authenticated to download large files. Now we need to identify the correct .gguf model from the repository. So once we have this file in our models folder, we attempt to run the model using llama.cpp binary. Sometimes we get certain issues, but we run the model with the correct codes. So let us begin doing this. So these are the different steps that we are going to follow. I am sure that when I will actually be doing the coding, you will be able to better understand. So let's start with creating the project folder. So when we start Hugging Face and we go to models, there are numerous models that we have. Each of them has its own speciality and its own competence. And Hugging Face is a platform that hosts all of these models like Qwen, OpenAI, Llama, NVIDIA. It hosts DeepSeek also, Cognito, Meta's Llama. Right? There are many models on Hugging Face. Now what we are going to do is that I have decided to use Qwen. Okay, see, DeepSeek is also there. But I thought I'll use this Qwen. Okay, and Qwen 2.5, it's an end-to-end, it's multimodal, right? Because our PDF can have images as well as text, images, audio, video, all of this it can. It's an end-to-end multimodal designed to perceive diverse modalities, right? These are the different key features that it has a novel architecture. It can use real-time video and voice chat. It has natural speech generation. It's strong performance. It's excellent end-to-end speech instruction is there. Right? So for now, I'm using Qwen 1.5. Okay. You can use 2.5 also, Qwen 1.5 also. That's just different versions. So okay. Now let's go to the code. So this is a model that I'm going to use from Hugging Face. Okay. So first, what we will do is we will open a new folder, and we will give it a name. Drag on a PDF. Okay. Now the first thing that we will be doing is we will clone llama.cpp. Okay, so what we will do is from GitHub we will clone llama.cpp because that is the backend with gguf format for local inference. So first we will clone it inside our project folder, okay, and build it. So I am opening a new terminal and I am just cloning this from GitHub llama.cpp get, and it will clone llama.cpp inside our project folder. Now we will change our directory to llama.cpp and we will build llama.cpp. Okay, so for this, first of all we will need to install CMake. After installing CMake, inside llama.cpp directory we need to create a folder of build. So we'll say make directory build and we will go inside build folder. Now we will generate the build files with CMake. And now what we are going to do is we'll build llama.cpp. So till now what all we have finished, we created new project folder, then inside our VS code we cloned llama.cpp. We downloaded open source llama.cpp project, which is nothing but a tool that lets us run LLMs like Qwen 2.5 locally on our computer without needing any cloud services. Then we tried building tried building it using make or CMake. Okay, and this gives us a working binary main to run our Qwen 2.5 models locally. So let's wait. Let's catch up once this is done. I'm pausing the video. Great. Now we have successfully built llama.cpp. That means our system is now ready to run Qwen 2.5 locally. Let's move ahead. Now we will grab the actual weights, model weights in .gguf format from Hugging Face. So first of all, what do we do is, we will first see it's still in build, right? So we need to go to our root folder and then we will create a mod folder for models. So we say make directory models and change directory to models. So here if you see, a new directory models has got created. Now we will download the Qwen 2.5 0.5b chat gguf model using curl. Okay, so let us try running the curl command from Hugging Face. This is the curl command from Hugging Face, the Qwen model. Okay, let's run this. Okay, so once we have done this and we run this curl command, we see that this is only 15%, right? Only, though it shows 100%, but it's only 15 billion that has come up. It means that there is something wrong in the way our file has got downloaded. And when I run this cat command, it says entry not found. It means definitely it has not got downloaded properly. I ran once again and still it just came to be 15%. So now 100% but 15B. But now what we will do is we will just go and manually do it from Hugging Face. So we have pip install Hugging Face underscore hub, and after that we'll log in Hugging Face CLI. It will ask for the Hugging Face token, which I have pasted, which will not be visible here, and as token we say no. So the logging was successful and the current active token is Qwen. So let's now download Qwen GGUF model using authenticated access. Okay, so now what I do is so now I'll create a file. I'll name it as download underscore Qwen.py. Okay, and here what I will do is I'll first say from Hugging Face import my this download, and then in this I'm going to say repo ID, my file name, my local, and those, right? Okay, so now this file that we have already created, now I will come out of my models folder and I will run python download .py. Okay, so this will download the Qwen GGUF folder model into models folder as we intended. Okay, now just confirming whether the model is downloaded or not properly, we will just say list -lh models. Okay, so here again we see that the 15 byte means that model has downloaded not properly. So I'll just remove my old file and I'll run this again. Just make this proper. Save it. Now let's run. Okay, there is a bit of change in the name. Instead of this name, let's go and change it, proper name. Now let's again run and see. Okay, so this is the correct name of the file. Okay, underscore underscore, I think somewhere I was doing wrong. So that is the correct name of the file. Let's change it. So now with the correct name changed, we have let's try this again now. Let's try one more last time. I hope this is the correct file now. Let's see if this works now. Let's continue running. Yippee! It will finally download the correct file. Sometimes you need patience. Done? That's fantastic. Let's see now. We just downloaded the correct Qwen 2.5 GGUF model, and that confirms that it is a real quantized GGUF model, not a broken one. Okay, let's just confirm this. Woohoo! We did it. So we got the full Qwen 0.5 GGUF model sitting safely and beautifully in our models folder. Okay. Now let's run it now with llama.cli. So let's go to llama.cpp build. And run this for inference test. Tell me some fun facts about moon. Okay. Let's check what the binaries were built. There are llama. There's no main over here, right? Binaries will be inside the bin folder, so let's change it to bin. We have llama.cli, right, in the bin folder. So let's run that now so we'll run Qwen using llama.cli. Let's be 100% sure of what is our path. Let's run this command. We are actually in a current location. We are trying to access models, but based on our earlier terminal path, it was a different one. So I need cd run this. working directory is this. We have a 388, which is complete and healthy, and the model is there. So finally we get it, and now we will see our model load with some token, vocabs and layers, and then Qwen will finally answer your question. Tell me a fun fact about the moon. Right? I can ask anything to Qwen now. We can say, thank you. Tell me who is India's PM. This is a bit. Okay, let me ask properly. Who is India's current Prime Minister? I don't think it is Justin Modi, isn't it? It's hallucinating, right? So it's officially it's hallucinating, right? And this is what we call hallucinations in LLMs. So why did this happen? That's because we are using Qwen 0.5b, which is a small 500 million parameter model. It's not fine-tuned on facts or Q&A. It's trained with basic general patterns, which is not specific knowledge, and it doesn't even have reinforcement learning from human feedback. So instead of refusing or giving the right answer, it just blends typical global political leader language into a totally made up response. What we can do now is we can upgrade it to a Qwen 1.8b or a Qwen 7b that is more accurate and less likely to hallucinate, or we can add a retrieval layer, which is RAG, use a vector database or structured fact lookup to ground the answer, and we can use prompt engineering to control all hallucinations, right? So let's start that, okay? But at least we are sure that our Qwen is definitely running locally now. Let's catch up with the next steps. Okay, so I'm just opening a new folder, making a new folder. I'm naming it as, say, RAG on PDF. Okay, I did it before, so let's name it something like this, PDF RAG. Okay, and I open the folder. Once I open the folder, I say yes, please trust the things. Now I'll just have a new terminal. And I will clone first of all llama.cpp. Because by cloning its GitHub repository into our project folder, this gives us the llama.cpp needed to run Qwen. So this command basically fetches the latest llama.cpp source code and creates a folder called llama.cpp in our project directory. The clone completes, let's see, yeah, it's completed. The next thing that we do is that we will move on and change our directory to llama.cpp. After this, we will install CMake. Once that is done, inside our llama.cpp directory, we will create a build folder and we will change our directory to build. After that, we generate the build files with CMake. And we will build llama.cpp. So far what all we have done is that we have created a new project folder. We opened the terminal inside, so everything happens in the right place from VS Code. Then we downloaded the open source llama.cpp project. This is a tool that allows you to run LLMs locally on your computer without needing cloud services. And we started using CMake to compile the project properly, which is the current way that we are working on. So this will give us a working binary main file to run our Qwen 2.5 models locally. So in the meanwhile this is happening, I can show you about a few other things. I can show you about where is this Qwen thing coming from. So if we go on Hugging Face and we see different models, there are a lot of models here. DeepSeek is there, Google Gemma is there, and a lot of other models are there. So if I search for Qwen and I can just go back so it will be able to. So this is the model that we have, Qwen 1.5. This is the model that we are going to use for chatting with our PDF. So Qwen 1.5 stands for Quantized Web Neural Network. This model is a language model that has been optimized and quantized for efficient usage, particularly for running on local machines using inference engines like llama.cpp. This 1.5 typically refers to the version number of this model. Now why is it used? I'm using it because it's efficient for model deployment. It has smaller sizes, it's a quantized model, so it has 500 million parameters only. Quantized version, yeah, so it's efficient in memory and faster in inference and quantization. It's cost effective because it runs locally, no additional, you don't have to call out for any cloud or API calls. Optimized for local hardware, we can do it fine-tuned, it is easily fine-tunable for specified tasks. We can have model control for specific needs. Then there is fast inference for real-time applications, like it has low latency, local running reduces API call delays, and efficient multitasking it helps. It is fine-grained, controlled over data. It is seamless integration into RAG systems. It works very well with RAG setups and accurate context-aware answers. and it's open source and community support, so free access to the model code and deployment. And lastly, it is scalable. It fits both small and large scale projects, so it can scale to handle larger workloads as required. So we are using the Qwen model. Now let's see how our code, where our code has reached. Okay, it's done. It's 100% built llama model. Now let's go and we're still in build, so we will go and just write our cd and change it to our main folder. Here we will create working directory. So now we have the models that is created, and we will go and download the Qwen 2.5 0.5 billion model. So hopefully it will happen. So we have downloaded it. Okay, so now what we will do is we will just check whether from inside our build there is no main folder, right? File, right? Okay, so what we will do is we will rebuild this case. Okay, it's there. We're just making, we're just trying to now let's see if it's there. Okay, inside the bin folder it might be there. So cd bin. Now let's see. If I run this, okay, let us try with llama. Not okay, still not there. Let us go and just try out with okay, it means our folder is there. Let us try and So we are here now, right? So our Qwen model is running well, but it is hallucinating, and that is why we are going and performing a RAG. Okay, so what I do is now I go and create a new file. Okay, uh, I name it as pdf chunker.py. Okay, now I have written the code. I will paste it here and then we will go through it line by line. Okay, so first what we are doing is, so this is the code. I'll save it first. Now what we are doing is, in the first step we are importing FIDs. Okay, this imports PyMuPDF library, which is also called FIDs, which is used to open PDF files and extract text and images from the pages. Next is we had defining load PDF text. This function reads all the text from a given PDF file and returns it as a long string. Here inside we are having the fids.openPDF path. It opens the PDF path and then it has the full PDF, initializes an empty string. Okay, then this thing will loop through each page, extract text content using get text, and it appends the text to full text and then returns the full text. So by now we have the entire PDF content as a big string. Okay, the second step is extracting images, which is from the PDF path. So this function scans the PDF, okay, and detects if any images are also present in it, because we are using OCR related. It doesn't only extract actual images file, it just adds like a caption placeholder for each image. Okay, so now we are having this fids.open path, and then image will be it opens the PDF again, this thing, and it prepares a list to hold the descriptions. Now in this line, for every page it gets all the images on that page. Okay, and here it adds a string like image on page 3. It's like a placeholder caption to image captions, and finally it will return the list of all image placeholders. So by now we know that where the images were in the PDF, but we are not using them in the pipeline unless we do OCR later on. Okay, the next is splitting the full text into overlapping chunks. So here we break the long PDF into smaller manageable chunks with overlap between them. Okay, so this is important for embeddings because models like ADA 0.02 have token limits. So inside the chunks and start.z equals to 0, the chunks are empty list to hold text segments, and start is where the current chunk starts in full text. Now this portion which is there here until we reach the end of the text, this is a loop. It defines a chunk from start to start plus chunk size, appends that chunk, moves the start index forward by chunk size to overlap 450 characters if the chunk size is 500, and overlap by 50. This gives overlapping chunks, okay, like 0 to 500, 450 to 95, 950, 900 to 1400, like this, and then return the chunk. The slide window option helps in overlapping, okay. So by now we have clean overlapping chunks ready for embeddings. And then this is just the main function. So in this step we read the full text, we scan the pages for images, we chunk the text into smaller parts with overlapping for semantic continuity. Okay, let's proceed to the next part. Okay, so now what I'll do is I'll have just brought up a moon.pdf, and you might like to see the PDF first. So in my moon.pdf I have this information. Moon is Earth's only satellite and the 5th largest satellite in the solar system. It's about 1/6 size. This much is the distance between Earth and Moon. It has no atmosphere. Its surface was covered with craters. Yeah, one of its theories, giant impact hypothesis, Apollo 11, all these things are there. And then we have the different phases. There's a photograph of different phases, and then we have different phases of this moon. So these are 2 pages of my moon.pdf file. Okay, now what do we do is we will actually I just ran it. So yeah, I just brought that moon.pdf and ran python pdf chunker.py. It's extracting the text, extracted the images options, chunked the text, and 4 chunks are saved to Python to output, and in output where is. So these are the different 4 chunks that are there. Okay. Fine. Now let's proceed. So what I'm going to do now is we have already done the PDF chunking. Now we will be doing embedding the chunks. Okay. So for this, what I will do is that I have the code with me, ready with me. So I will just finish writing, and I have pasted it here. Let's see now what this code is doing line by line. So we first of all import OS and have the paths, operations, environment, access. I have my .env OpenAI stored in .env file, which will be accessed in embed chunks because we are going to use OpenAI embeddings. Then I am using this fits. It allows us to open the PDF file, read the text, and detect images page by page. Then from .env we import .env. So this basically loads our .env files to ensure access of our API keys or any config settings which are there in the .env file. Then from OpenAI we import OpenAI and import the official OpenAI Python client. So we know that we can call the embedding API from there. Then we load the .env. Right, our OpenAI key is there in our .env file. Then we go and make the client. It initializes the OpenAI client, automatically uses the OpenAI API key from our environment. Then let's see the functions. The first function is extracting the text and the images. Extracting text and images, we first of all parse the PDF. The full text is there. It will store all the extracted text, and image captions is there. It is nothing but it has a placeholder strings for images. Now inside this function, we open the PDF file located at this particular PDF file. Now these two are nothing but it is initializing, right, the two empty containers. After this we have the full 4-page, this loop is there. This loop, it loops through each page in the PDF and extracts plain text. Now comes this part, the images. It gets a list of all image metadata on that page. Then for image index, now here in this loop, instead of extracting the actual image data, it stores a placeholder string, okay, like this. And finally we will return the full text and image captions. So this returns the two things, all the text and a list of all the image captions. Both will be passed for chunking and embedding later. Let's see the next function. Inside this function we have chunks equals to this empty list and start equals to 0. This is nothing but empty list to store all the chunks, and start defines where each chunk begins. Then this loop that we have, it is nothing but it says, like for example, the chunk size is 500, okay, and the overlap is 50. So you get chunks like chunk 1 will be characters 0 to 499, chunk 2 will be characters 450 to 949, chunk 3 will be characters 900 to 1399, like this. This ensures continuity in the meaning across boundaries, okay. And then we return the chunks, the list of text chunks. Now let's see the next function, which is the get embedding function. It basically sends a single chunk to OpenAI and gets 1536 dimensional vectors back, okay. So here when we have this response equals to client.embeddings, this calls the OpenAI embedding API with the input chunk, and finally we return the vector. This vector represents nothing but the semantic meaning of the chunk. Then is the generate embeddings function. It loops through all the text chunks and image captions and embeds them one by one. This embed data which is there, it is nothing but a list that will hold dictionaries, okay, like chunk ID, text, embeddings, something like that. And for I equals to this entire loop is there, it loops through each chunk and prints the progress as it goes. So this particular thing stores each embeddings and the original text and an ID. And finally it returns a list of all embedded chunks which are ready to be saved, okay. And then this is your main function. Okay, so now let's run this file and see. I'll open the terminal and I will say python embed chunks.py. This confirms that our Python script is running properly in the main block. We saw that now the raw text length, that is 1454, and this shows that the total number of characters extracted from this moon.pdf was 1454. This is like a text only content, right? Everything from headings, paragraphs, tables, etc., from all pages. And the pdf, the number of images is 1, each stored right in the placeholder, right? And then these are added as searchable chunks, so our chatbot can still respond to the questions. And then we have the total chunks equals to 5. This is nothing but the total number of chunks that will be embedded. So these are the embeddings that are generated. So a total of 5 unique semantic units are there, and this is nothing but it shows us the progress while we are calling OpenAI embeddings API 5 times, 1 for each chunk. Each time this line gets printed, right? This embedding, this line is getting printed here, okay? And then finally all the chunk embeddings are stored safely into our embedded chunks.json. And inside our embedded chunks.json we see something like this. It is nothing but it includes chunk id, which is an index number. It includes the actual text, and or it includes an image caption, and it includes the numerical vector representation. Okay, so this is nothing but embed chunks. Now let us go and make another file called as searchchunks.py. Okay, I'm going to tell you about a few things on chunking. So in our code, especially in this PDF on embed chunks.py, we see this chunking logic. Okay, and this says that this is nothing but a sliding window approach. Okay, so it's basically very super straightforward. Okay, we break the documents into small blocks, each 500 characters, and then make sure that there's some overlap, like 50 characters between the chunks. And why do we do that? Because imagine that there's an important sentence that starts at the end of one chunk and ends in the next. Okay, so if it didn't overlap, the meaning would be split and the model wouldn't understand what's going on. So by overlapping slightly, we make sure that the full idea stays within at least one chunk. So yes, we do repeat some text and technically increase the number of tokens, which means slightly higher cost when generating embeddings, but the trade-off is that we get much better accuracy, especially when a user asks something that spans across multiple sections. Okay, so now apart from this, there are a couple of other chunking strategies that we can use, and I'll discuss these also with you. Okay, so let's see. Now there are fixed size chunking. Okay, then there is recursive splitting. Yeah, these are different other two types of chunking that we know. The simplest way is fixed size chunking. So you just chop up the text into equal sized blocks, no overlap, no logic, just raw divisions. Like for example, we break 1000 characters or 200 characters and just move on. It's super fast, it's easy to implement, but there is a big downside that it doesn't respect your meaning. You might cut out a sentence or even a word right in the middle, yeah, which really messes up the model's understanding. Okay, so that's why this is better for logs or raw CSVs or data where already it's isolated line by line. So we didn't use this because in our PDF narrative, right, because we need context. And another is recursive splitting. So recursive splitting, the is something we are definitely considering in our future upgrades too. Yes, I was thinking about the recursive splitting. The other most intelligent way is recursive splitting, and we will definitely be using it for the future also. In this approach, basically the document is broken down logically based on actual sentence, boundaries, paragraphs, or even section headers. So tools like LangChain's recursive character text splitter or even Spacey with sentence parsing can actually help here. So this way you get clean, coherent chunks. So each one is complete and meaningful on its own, right? So you minimize hallucinations, reduce token usage, and even make the whole interaction more natural. Uh, let's use it in some other project. Right now we are using a sliding window approach because it gives us a context continuity. Okay, recursive splitting is smarter and cleaner, but it's ideal for semantic rich documents, especially in the production environment. And fixed size chunking is fast, but it is risky because you might lose out on you know the meaning, the actual context, and semantic meaning. So the way you basically chunk your text really shapes up everything that you follow, the embeddings, retrieval, even hallucination control. So choosing your right chunking strategy is one of the most important things, and it has a very huge impact on the final user experience. Okay, thank you so much. Now we will have another file called as search chunks. We have finished with the embeddings, and now we will do the search part. So I have just created one search chunks.py, and in this I'll paste the search part or the chunks. Let's understand each line by line. So we will now first of all create a collection named PDF chunks. Okay, and this PDF chunks in ChromaDB to store all the embedded text chunks. Okay, and here in this particular line of Chroma client, what we are doing is we are now setting up Chroma client to use an in-memory configuration for prototyping, quick prototyping. Okay, now in this portion what we are going to do is this loop actually adds each chunk to our ChromaDB collection. It uses chunks ID, original text, and its vector embeddings, and we store them all one by one. Okay, and then in this chat history we initialize an empty list to store our chat turns, both query and context that matched it. Now let's see in this particular thing what really happens. This actually begins a live interactive session in the terminal. Okay, it takes the input from the user until the user types exit. Okay, the next part is this part, wherein what we are going to do is this each query, so whatever for each query that comes from the user, we call the text embeddings ADA 0002 model and convert the text into a semantic vector. So this is the same model that was used for the original PDF chunks also, right? So it will ensure compatibility. So for each query we call this text embedding ADA 002 model and convert the text into a semantic vector. Now in this portion, here we pass the query vector that we got to ChromaDB and retrieve the most relevant chunk for our collection. Just I'm doing the 00, it means I'm just taking the top one right now. So it is 1. So the topmost matched relevant chunk will be coming as the matched chunk. Now in this part, we will now store the current turn, the matched context, and the user question into our chat history list. Then this is where comes the prompt engineering part. Here we construct a multi-turn prompt by looping all over all the turns. For each, we include the retrieved content and question, and we leave the answer field blank. Okay, because that's what LLM will fill in. Okay, then in this it's simple. We will just write the complete prompt to a file, and the idea is to then run my Qwen, which is locally or locally done using this prompt to generate the actual answer. And finally, we will let the user know that the prompt is ready and stored in a text file. They can now run Qwen over this prompt to complete the response generation. Okay, so this script basically sets up a full loop embedding retrieval, multi-turn memory, prompt construction, and a file persistence, all designed to work with a local or external model like Qwen for final answer generation. Let me know if you want any other explanation on this. Fine. Okay, thank you. Hello. So far we have completed the core backend logic of our system. In PDF chunker.py, we handled parsing the uploaded PDF, extracting both plain text and image blocks. Then in embed chunks.py, we generated semantic embeddings for those chunks using OpenAI's text embedding ADA002 model and stored them in ChromaDB vector collection. After that, our search chunks.py module allows us to semantically query ChromaDB to fetch the most relevant chunk, either from the document text or OCR based image content, depending on the user query. Now we are moving on to building the main interactive layer, which is app.py. This is where all the components come together through a user-facing interface building with Streamlit. So, the goal is to allow the users to upload PDFs, ask natural language questions, and receive content-aware responses powered by either a local LLM like Qwen via llama.cpp or OpenAI's GPT model. So let me take you through the app.py. Okay, so I have the code with me ready when I was working on this project. I'll take this and I will make another file here in our we'll make this app.py and I'll explain you every single line of code. Okay, so first of all, we have these Streamlit and different other libraries that we are going to import. Okay, later on we load our environment variables and initialize OpenAI's API key. Okay, then the load env and client OpenAI. This gives us access to the models like text embedding, ADA002 and GPT for completions. Next we will set up the ChromaDB in a persistent mode so that it retains data across sessions. So we are using a local folder called .chromadb, okay, and to store in it. So then we create or retrieve a collection named chat_pdf. This is where we'll store our PDF chunks and their embeddings. Okay. Now comes one of our core functions, extracting both the images and images from the PDF. Okay. Text and images from our PDF. So we first of all open the file using PyMuPDF. Okay. Then iterate over each page. Then for each page we grab all the textual content and concatenate it into one big string. Then for every image on that page we extract the raw image data, convert it into a usable format with PIL, and then run OCR on it using Tesseract. Finally, we store each image's OCR result along with the page and index number. That way we can store the image back to the user. We can show the image back to the user later during chat. Okay. Now now let's go further. In this particular function, this breaks a large piece of PDF to text into smaller and overlapping segments. We initialize a list called chunks. We use a sliding window technique here and take the max tokens from the current start position. So then after each chunk we move forward by maximum tokens minus overlap in order to overlap to ensure the overlap. So this overlap is actually crucial because it preserves context between segments, and we return a list of strings finally because it preserves context between segments. Okay. Return of string segments ready for getting embedded. Okay. Now let's go to the next function, which is get embeddings. This one's pretty straightforward. We are just calling OpenAI's text embedding ADA 002 model. We pass it as a chunk, or we pass it a chunk of text, and it returns a long list of numbers, that is the vector that represents the text semantically. Okay, that's what we will be using similarity search later. Let's go to the next function, embed chunks. So here I am preparing everything for search. First I am checking that there is any old data in ChromaDB and delete it to keep things clean. Okay. Now then I combine all the text and image chunks. I store it in ChromaDB and I tag it with metadata like what page it came from, or whether it is an image or it is a chunk. Okay. Once this is done, then my entire document, both plain text and OCR from images, is now indexed and searchable semantically. Understood? Okay. Let's proceed to the next part, which is the search top chunk function. Okay. So in this function actually is where the magic happens. When a user asks question, So here first I convert the user's query into an embedding vector, just like I did for the document chunks. Then I use ChromaDB to do a similarity search. Now here's the most important part. If the user is asking about an image, like what does this diagram show, then I only search among the image based chunks. Otherwise I search in plain text. ChromaDB gives me back the top match. I extract both the actual chunk of the text or OCR and the metadata like page number and whether it's text or image. This chunk is what we'll use to build the prompt for Qwen or GPT. Okay? Let's go to the next function. So this is where I build the final prompt that we will send to the LLM, whether it is OpenAI or Qwen. So at the top I give it some initial instructions, like I basically tell the assistant how to behave. I mentioned that if the chunk is from an image, it shouldn't say I can't see the image because the user already sees it, right? Then I loop through the entire conversation history. For each past history, I check the type, was this chunk from the text or image. I clean up the chunk by stripping extra spaces. Then if it's an image or chunk, I tag it like image from page X. And I add a little extra instruction so that the assistant knows it's an OCR text from a visible image. Then I add the actual context text, the user question, and leave the space for the answer. So by the end, this prompt looks like a full dialogue, a series of context, question, answer that helps the model answer naturally and consistently. Let's proceed to the next function. So this function is responsible for running the Qwen model locally using the llama CLI binary. I pass it the final prompt and get back the generated output. Okay, so like here I'm using the try except block, okay, to safely handle timeouts or runtime errors when calling the subprocesses. Then in this with open thing, the first thing I do is save the prompt to a text called finalprompt.txt. This is because llama.cpp CLI expects a file input using the -f argument, so I prepare it right here. Okay, then in this block, which is the result subprocess block, I now call the Qwen model using subprocess.run. So I pass in the full command llama and -CLI in the binary, -m points to the Qwen gguf model file, and -f points to the prompt file we just saved. Then this CWD that you are seeing, I also set the working directory to llama.cpp build, because that's where the executable is located after the llama.cpp. And finally, capture output equals to true. This I capture the standard output and error from the subprocess so that I can read the model's response in Python. And this text equals to true. Finally, this ensures that the output is returned as a decoded string, not raw bytes, making it easier to handle later. Then my timeout equals to 90 is because to avoid the model handling forever, I set a timeout of 90 seconds. If Qwen takes longer than this, the subprocess will raise a timeout exception. And finally, once the subprocess finishes, okay, this parse output, I grab the output standard output and clean it up with .strip and send it to my parse Qwen output function to extract just the actual answer. Then this accept this process, this line. If the subprocess times out, I return a friendly message saying that Qwen took long. Okay. And if there's any other kind of error like a file not found or model crash, I catch it and return the actual error message so I know what went wrong. Okay, let's proceed. This function now sends the final prompt to Qwen OpenAI's GPT-3.5 model and returns the response. It's used when the user selects the OpenAI option instead of the local Qwen model. Okay. So again, I wrap the entire call in a try except block to handle any potential API or network calls. Here in the response line equals to client.chat, this one. Here I am calling OpenAI's chat.completion.create method. Okay. And this is the endpoint used for chat based models like GPT 3.5 Turbo. Model is GPT 3.5 Turbo, and I specify that I want to use GPT 3.5 Turbo model, which is the cost effective and fast, perfect for this kind of document Q&A use case. Messages, of course, now you'll have a role, a user, and a content in the prompt. I wrap the prompt inside a message list, and this tells OpenAI that the user is saying this, the model should respond accordingly. So using this chat format like this is required for GPT chat models actually. My temperature is 0.07, so I set the temperature to 0.07 to give slightly creative and natural responses but still stay mostly grounded. A temperature of 0 would be too robotic, higher than 0.7 risks hallucinations. Okay. That now I extract in the return the content of the first response choice from the model and return it. My dot strip will remove any leading or trailing white spaces to keep the things very clean. And finally, if anything goes wrong, then like API key is invalid, internet is down, or OpenAI returns an error, then I catch it and return a clean error message showing what happened. Okay. Now this parse Qwen function that we see and the is image query function that we see, right? These are the two query functions that now we will look at. So the parse Qwen output function, this function is a simple cleanup for the raw output we get back from Qwen. So Qwen sometimes includes a lot of extra stuff in its output, like maybe debug logs or prompt echoes or formatting instructions. So what I do is that I split the entire output of the keyword answer. This works because my prompt ends with that exact word, right? So I expect that the model to start generating the answer right after that. Then I check if the answer was actually found, like meaning the list parts has more than one element. I return the last part and strip out any trailing white space. So if the answer wasn't found, I just return a fallback message saying Qwen did not answer or generate a proper answer. Right? So this function ensures that I am not only extracting the final answer part from Qwen's full standard out, clean and reliable. Okay. Next is image function. So this one is a super straightforward, and it's like a smart little filter to check if the user is asking about something visual. So I have list of keywords like image, diagram, figure, visual, picture, etc. So I then just I just lowercase the user's query and check if any of those keywords appear in. So if they do, then that means that the user probably wants to reference any image, so I return true. If not, then it's a regular text query, so I return false. So this helps me route the semantic search later. If it is an image query, I only search in image OCR chunks. Otherwise, I search in plain text chunks. Okay, let's proceed. Let's see this set.sage page. Now this is actually the Streamlit web application. So I start by setting up the Streamlit page config. I give the app a title and set the layout to wide. So the interface has more breathing room and looks better, especially when showing chats and images side by side. Okay. Then comes title. This line just displays the main title of the app at the top. It tells the user exactly what is the tool about, like chatting with both text and images extracted from a PDF. Now comes in the model choice. So then I show a horizontal radio button, giving the user the choice between using Qwen or local OpenAI's GPT-3 3.5. And this is super useful for switching between fast, cheap, local generation and more powerful cloud resources. Then comes the PDF file upload widget. So this line displays a file uploader where the user can drag and drop a PDF file. So once they upload, the backend kicks off the extraction and indexing processes. If the PDF is uploaded, okay, then once that is done, I show a spinner to let the user know we are working on extracting everything from it, both plain text and any images with embedded text. Okay, so this text image blocks that you are seeing, all that comes in from there. Okay, this function actually handles heavy lifting. It reads the PDF, pulls out the plain text, also runs OCR on any images to extract text from those as well. Then comes image map. So I create a dictionary where each image is indexed by its page number and index. So later on, when we want to display an image in the chat, we can grab it quickly from this map. Then this text chunks. Here I break the full PDF into smaller overlapping chunks and tag them as typed text. So these chunks are easier to be embedded and search and can search semantically later. Then this image OCR chunks. This filters out images that have valid OCR text and wraps them in a structured format, like tagged as image, and we store their page and index too, so we can trace them back visually. Okay, then comes embed chunks. So once we have our text, the image OCR chunks ready, we embed them into ChromaDB. This step makes them searchable later when the user asks a question. If chat history not in state session, so this here I set up a persistent chat history using Streamlit session state. This helps me track multiple rounds of conversation, which is essential for multi-turn dialogue and building a complete prompt. Now comes user input. So if this is the chatbot, okay, ask something, this one. The user can ask anything here, what's the budget mentioned on page 2, or what does the diagram on page 4 show, and we will handle it all. Now if the user input this loop, once the user types a question, I check whether it's image related, like if they use words like show or diagram. If yes, I'll only search the image based chunks. Then in this top meta top uh, chunk, here I perform semantic search in ChromaDB to find the most relevant chunk, either from text or image OCR based on the user query. Then this part, here I save full turn the user's query, the matched chunk and its metadata to chat history. This helps us build full prompts for multi-turn conversations. Then is this prompt build. Now I use the entire chat history to build a well formatted prompt, including context and questions from each turn that will pass to the language model. Now comes if this model Qwen. Here I check that when the user selected if it's Qwen, I run the prompt locally using llama.cpp. Otherwise, I'll run OpenAI's GPT-3.5 and return the response from cloud. Okay. And finally, in this session's chat history, after getting the answer, I attach it to the last item in the chat history, so it shows up in the interface. Now this part for turn thing, now I start looping through the chat history to display it on screen. First I show the user's question. Now this part this is the final part. So if the matched chunk was from an image, I fetch and show the image in the chat so the user can actually see the visual context. And here in this markdown thing, finally I show the assistant's answer just under the image and text completing the entire loop. Okay, so this entire file I have explained you, this entire UI block, okay, makes our app fully interactive from upload to Q&A and smart enough to handle both image and text content from any document. Okay, in the next part now I will actually run this. In fact, I can actually even try out now. Let's just open the terminal and just say so. Now let's go and start with testing our code. We'll say Streamlit run app.py. It opens up browser. Now let us pull up the file, our moon.pdf. I'll show you what's there in the moon.pdf. This is the moon.pdf. It consists of some information about moon, distance of moon and earth. It has no atmosphere. Its surface is covered with craters, which were formed by meteor impacts. It talks about the giant impact hypothesis. It talks about moon missions like Apollo 11. It talks about this particular image and says about the phases of different moon, and it then also talks about what are the names of these phases of different phases of the moon. So, and it says that the cycle repeats a month after about 29.5 days. So let's ask questions based on this particular PDF. Now first of all, what I'm going to do is that I'm going to show you how Qwen runs. Actually, Qwen will run very, very slow, okay, because it's loaded on my laptop. right? It's a local LLM. So if I ask, show me the image or picture of the different phases of the moon. Now it's running, okay, and it keeps running. It is 12:26 right now, and let's meet in a while. Here we are. Okay, so now it actually failed, okay, and then we are falling back to OpenAI now. Okay, so instead of that, what we can do is we can just select OpenAI from start itself, because whenever you are going to use a local LLM, okay, it is going to result into a few challenges. So when I use OpenAI, suppose I say just hi. Okay, how can I assist you today? Okay, show me or explain the different phases of the moon. Let's ask. Since it's OpenAI, it came like a very quick, right? It is saying new moon first quarter. Then if you remember, there was another thing in our PDF which mentioned about how many how many days the cycle repeats. So let's ask, how many days the cycle repeats. It has to answer 29.5 days. Let's see whether it has been able to extract the number properly or not. Wonderful, it's doing a very good job. Now let's ask something not related to the PDF, and it should answer like I don't know or something like that, right? Because it shouldn't use OpenAI's brain for answering our question. So maybe I'll ask, who is the Prime Minister of India? Let's see. This information was not there in our moon.pdf. So I'm really happy that it said that I cannot provide real-time information such as current Prime Minister of India. So you see that our chatbot is really working very nice. It's giving us the images, it is explaining the images, okay, it's also not hallucinating, it's extracting numbers very much properly. So this is doing a very wonderful job. Now here, see, I made a bit of a change, okay, in this run OpenAI completion. So where we saw that Qwen was failing, I wanted to shift it to OpenAI so that it becomes easier for the user. Otherwise, it would take a very long time. So I let the user actually choose, right, whether they want to run their query using Qwen locally or OpenAI remotely. But Qwen, since it runs locally via llama.cpp, might sometimes fail and it can time out. It can hang or it can crash if the prompt is too long, or even if the system is under load. So I wrap that logic like this. So if here how it works is that if I try to run the Qwen model, okay, it uses the prompt that we just built. If the output contains any warning like Qwen timed out or Qwen generation failed, I immediately show the user a small notice using Streamlit's st.warning. Then I gracefully fall back to OpenAI, same prompt, just routed through GPT 3.5 Turbo API. So this way, even if local generations break, the user still gets an answer without interface freezing or erroring out. So it gives the flexibility of running locally to save cost while still being reliable enough for production style usage. Okay, so this is the one change that I had made after I finished discussing app.py. Okay. So see, one of the key challenges when using OpenAI in production, especially in an interactive app like what we created, where queries are dynamic, is actually cost management. So right now, every single user question triggers a new OpenAI call. And we also recompute embeddings from scratch every time the PDF is uploaded. When functionally everything works beautifully, it's not optimized for cost, especially when scaled to more users or larger documents. So, to bring costs down, I'm going to discuss with you some improvements that we can further in future make to our project. The first is implement a KV caching for OpenAI responses. The first and the most impactful change is to introduce key value caching for OpenAI responses. Right now, if the user asks the same question twice, even within the same session, we hit the OpenAI API again and again. That's not necessary. So, we can use a simple in memory dictionary or ideally Redis to store past queries and their responses. Next time the same prompt comes in, we skip the API call and return the cached response instantly without any tokens, spending any tokens. The next method is cache embeddings instead of recomputing them. Okay, so right now we embedded every text chunk and image OCR chunk from scratch each time a PDF is uploaded, even if it's the same document. That's a little hidden cost, and it adds up when we use OpenAI's text embedding ADA002. So we can fix this by caching embeddings using a hash of the chunk text as a key. If the same chunk comes again, we just load the stored embedding. This cuts down embedding costs significantly, especially in reused or shared documents. Next, let us see about use Redis for persistent multi-user caching. So to make caching scalable across sessions or users, we can plug in Redis. This way, even if the server restarts or a new user comes in, we still reuse past embeddings and responses. Redis will act as our persistent memory, perfect for storing cached embeddings, cached prompt response pairs, and session level chat history. Next is trim and compress prompts to reduce low token usage. Another optimization is to keep our OpenAI prompt size under control. So currently we pass the full text history and large chunks of OCR, which adds a lot of tokens per call. Instead, we can only include the most recent one or two turns in a prompt. Then we can strip redundant white spaces. We can use concise summary instead of full chunks when possible. So this keeps the prompt length minimal, which directly reduces cost since OpenAI charges per token. Next is use pre-computed answers for common queries. Or I can talk about fallback to OpenAI. So finally, in our latest version, we already implemented a small fallback mechanism. We first try answering with the local Qwen model and only call OpenAI if Qwen times out or fails. That already cuts OpenAI usage by a huge margin. We can further extend this by allowing admins to control fallback frequently or rate limit usage for heavy users. So, finally, these changes like caching, prompt control, smart fallback, pre-computation together can help us maintain a seamless user experience while significantly reducing token costs. They are practical, they are scalable, and easy to plug into our current architecture. They'll also help our app sustainably grow. It was a very nice discussion. I hope you have learnt a lot today. Thank you for being with me till here. Do use the code and try running the code yourself. I have explained each and every line of the code and go through the entire YouTube video. And in case you find out any other question or any other better methods, please comment. This was Charmi. Thank you so much.